Hello everyone, we are Group 95 presenting for CS771 on the paper by Mohammad Rostami titled Lifelong Domain Adaptation via Consolidated Internal Distribution. Deep neural networks excel at automatic feature learning and classification through end-to-end training. However, robust generalization on unseen data remains a challenge, particularly under domain shift, where training and testing data distributions differ. In this presentation, we will develop an algorithm to address unsupervised domain adaptation in continual learning settings. The goal is to update a model continually to learn distributional shifts across sequentially arriving tasks with unlabeled data while retaining the knowledge about the past learned tasks. Our solution is based on consolidating the learned internal distributions for improving model generalization on new domains and benefiting from experience replay to overcome catastrophic forgetting. Before we dive into the proposed solution, let's first understand the key challenges for achieving robust generalization in deep learning. Deep neural networks are highly effective at identifying intricate patterns in large datasets, allowing them to automate feature extraction and classification. However, DNNs often overfit to the source domain, meaning they become too specialized in the data they were trained on and struggle to perform well on new unseen data. Domain shift occurs when the distribution of data changes between the training phase and real-world testing, as seen when models are deployed in new environments or with different data sources. Under domain shift, DNNs tend to fail in producing accurate predictions, making robust generalization a key challenge in fields like autonomous driving, healthcare, diagnostics, and finance. Existing continual learning algorithms also face challenges when it comes to unlabeled datasets. Continual learning refers to the ability to learn from non-stationary information streams incrementally. Non-stationary represents continuously changing data distributions. Incremental learning refers to preserving previous knowledge while continuously learning new information. In continual learning settings, models must adapt to a sequence of tasks or domains over time, each with unique characteristics. Traditional supervised learning methods are inefficient for CL as they require fully labeled data and complete retraining, which is often impractical for evolving data streams. Most current CL algorithms focus on tasks or domains that have fully labeled datasets. As a result, they rely on extensive data labeling for each new domain encountered. However, manual data and annotation is often impractical as it is both time-consuming and costly. UDA or unsupervised domain adaptation is therefore relevant to our problem as it aims to train a model on targeted domain with unannotated data by transferring knowledge from a source domain that has labeled data. This can be achieved in two ways. Shared latent space alignment. Many UDA methods align the data distributions of both the source and target domains in a shared embedding space, allowing a classifier trained on the source domain to generalize to the target domain. Domain alignment techniques. Domain alignment can be achieved through generative adversarial learning or by directly minimizing the distance between the two distributions. However, UDA algorithms face a challenge of catastrophic forgetting. Traditional UDA methods are not suitable for continual learning because they typically require access to both source and target datasets simultaneously and often only handle a single target and source domain. Simply updating the model for each new domain can lead to catastrophic forgetting, where the network loses information from previously learned domains due to retroactive interference. Our new proposed model is an algorithm that aims to enable lifelong unsupervised adaptation of a model to new domains with only unannotated data. This means the model can continuously learn from changing environments without labeled data. The core idea is internal distribution consolidation. The approach consolidates the internal representation or distribution learned by the model from the initial source domain, where labeled data is available. The internal distribution acts as a memory of learned knowledge and helps the model adapt new unlabeled domains. Multimodal distributions for coupled learning. By treating this internal representation as a multimodal distribution, the algorithm updates the model to ensure that the knowledge from original domain is coupled with the new domains it encounters. This coupling allows the model to generalize effectively across multiple unseen domains. Addressing catastrophic forgetting with experience replay. To prevent the model from forgetting past knowledge, it saves key representative samples from previous tasks. When learning new tasks, it replays these samples, reinforcing past knowledge as it adapts to new data.
Problem statement. Source domain setup. We start with the source domain S, where we have a labeled training dataset D is equal to x0, y0. This dataset is drawn from an unknown distribution P0 of x, and we can train a deep neural network f of theta on this data using empirical risk minimization, which minimizes the classification error between predicted and actual labels on the source domain. If the dataset is large and the network is complex enough, the model will generalize well on new samples from the same distribution P0 of x. Challenge of continual learning. In continual learning, we face the additional challenge that the input distribution is not stationary. Over time, the data distribution may shift, leading to a distributional gap or domain shift between the training data distribution and the new incoming data. If the model is not adapted to these changes, it may perform poorly on the new shifted data. Sequential target domains. To simulate real-world scenarios, we consider a series of target domains TT, each with an unlabeled dataset DTT equal to XT. The samples in each target domain are drawn from different distribution PT of X, meaning that the data distribution changes over time. Since these datasets are unlabeled, we can't use standard ERM methods which rely on labeled data for training. To address domain shift and catastrophic forgetting, we decompose our network into deep encoder 5e, which maps data to an embedding space Z and a classifier HW. After training on the source domain, the classes are well separated in Z. Our goal is to maintain the separation as new unlabeled target domains are introduced, allowing the model to generalize to new domains. We achieve this by keeping the distribution in Z stable across domains, minimizing the distance between the source and target distributions in Z. That is, between distribution phi of P0 of x0 and phi of PT of xt is minimized. However, unlike standard UDA methods, we can't directly access the source data during continual learning, which makes it challenging to align distribution without forgetting past knowledge. Proposed solution. The solution described involves learning a discriminative embedding space for a model that consolidates intermediate distribution to improve generalizability. The encoder maps the input source distribution into a multimodal distribution Pj of Z in the embedding space, with each mode representing a class. Data points from a specific class are mapped to the corresponding cluster in the embedding space. To model the learned distribution, Gaussian mixture model is used, which consists of KKK components. The model is defined by the given expression, where alpha j are the mixture weights and mu j and sigma j are the mean and covariance for the components respectively. Since the class labels are available, the parameters for each mode can be computed independently using maximum a posteriori estimates. For each mode j, the support set Sj consists of data points belonging to that class. The map estimates for the GMM parameters are given. Theoretical analysis. In the PSE learning framework, this theorem provides a bound on the expected error a classifier will experience on new unseen tasks based on previous learning experiences and data distribution changes across tasks. Specifically, it considers a set of possible classifiers or hypothesis class and describes the errors. E0 for the initial domain, ET for the target domains, and ETJ for a pseudo dataset that approximates target performance. The theorem then relates the error on target domains to several factors including the pseudo dataset error, the difference in data distribution between consecutive tasks, an ideal error bound achievable by an optimal classifier, and an additional residual error term. By accounting for these elements, the theorem provides insight into how well the classifier can adapt to new tasks while retaining past knowledge, thus helping guide continual learning by limiting error as tasks evolve. Theorem 1 explains why LDAUCAD algorithm is effective. Major terms on the right hand side of equation 5 as an upper bound for the expected error for each task domain are continually minimized by LDAUCAD. The first term is minimized because the internal distribution random samples are used to minimize empirical error term as the first term of equation 4. The second term is minimized as the third term of equation 4 when the task distribution is aligned with the empirical internal distribution in the embedding space at time t. The third term, which is a summation, which models the effect.
So now coming on to empirical validation. So yes, so we will be using different type of datasets for different tasks and we'll validate this model. So for digit recognition, we'll be using MNIST, USPS and SPHN in such sequential order. Similarly for image clef T, we will be using these models. For the office part, we'll be using these models, and for office cat, we'll be using these models. Now coming on to the network structure and evaluation protocol. So this is the protocol we follow to evaluate our model on different datasets. So for we'll be using VGG16, which is the basic CNN model, which works very well for image classification, and for image clef we'll be using ResNet50, which works good for this dataset. And now we'll generate performance curves like these with accuracy versus epochs, and we'll take a mean of like 5 runs for the accuracy, and these are different domains like by red and by blue and by black, like different colors show different domains. Okay, so yes, these are the model. models also. And now we'll share on some results from these curves. So we see that we have trained the model for 100 epochs on each task. The experience replay, which is like the past information which the model uses, will use 10 samples per class per domain. Domain shift. Yes, so when we change the domain, there's less knowledge about the new domain by the model. So as you can see, a drop in the accuracy between the two domains in almost all the curves. Okay, and uh, now the algorithm effectiveness. Now the algorithm works really well. Like it minimizes forgetting. Like it keeps in check the past information, but there is still some drop in accuracy because of the change in domain of the dataset. And in some datasets, like for this one, there's a big drop. Like this is the office home dataset. There's a big drop. Why is there a big drop? There's a big drop because there's a large gap between the two domains. Okay, and in some models there is some catastrophic forgetting. Suppose the SVHN dataset, that is also because there's some domain difference. Now, if we compare it with the classic UDA, see here, you can see the different accuracies. So we see the LDA usage algorithm completely beats the normal UDA algorithm, and it works very well, and it keeps in check with the past information, and it minimizes forgetting. So that is a plus point of this algorithm. Like it is good for unsupervised domain adaptation. Like it adapts, keeping in check the past past data sets, past data. Okay. Now the analytic and imperative study. So from the above data also we get similar conclusions. Like it works well for image clef DA dataset, which is a balanced dataset. There's not a big gap between the two domains, but it does not work so well for the office home dataset where there's a domain gap because it is not able to adapt that well in comparison to other datasets, in comparison to other models for this similar task. And for the office category dataset also, this is a balanced dataset, so yes, it works well. Now, this is the visual representation of our model, so we can see this is what a digit recognition task. Okay, and each color shows a different digit. And as you can see, when this is the initial, like the t is equal to 0 part is the initial, where there is no, like there's only the label dataset that is written in the model, and we can see there's a rough classification of different digits. Now if we add on, like for the second row we have added on SPHN and MNIST, so we can see like the model refines itself even further, and we can see a better classification of the digits. And in the last one we can see the model refines itself even better. Like the classification task is done very well in the last row. So like yes, so we can see the differences in the row, and we can see how it preserves the previous information going on to the next information. That we can see how well this LDA user algorithm works. So now coming on to the catastrophic forgetting mitigation. Yes, so it retains knowledge. As you can see, it does not forget. Like from t is equal to 1 and t is equal to 2, it does not forget. Like even as the new part is added, it would refine itself even more, not forgetting the past data it trained on. Now the alignment of data distribution. So as you can see above, we use the Gaussian mixture model. So yes, it actually gives us something similar to internally Gaussian mixture model distribution. And we can see that MNIST distribution increasingly resembles that of the SVHN. So yes, they both resemble because the source domain. This supports, yes, this shows how this algorithm keeps in check of the past information and works well. Also for the hyperparameter sensitivity, we can see that this model depends on lambda and tau, as discussed earlier. Lambda is a trade-off parameter. So this lambda has almost minimum effect on performance because of empirical risk minimization, because of the loss term is relatively small at the start, making lambda less critical for fine tuning. Now the tau, which is the confidence parameter, it controls the confidence in the alignment process. So when this is 10 to 1, the model performs better, which is evident from the earlier algorithm. And this is due to reduction of label pollution. Yes, now the label is polluted less because we are more confident. So when tau is equal to 1, yes. So when tau is equal to 1, the model becomes more robust to such outliers. Now coming on to empirical support for theoretical analysis. Now this observed result also aligns with the theoretical result we presented, which is good. And the overall conclusion is that the empirical evaluations that the LDA usage method, it works as expected, demonstrating effective, yes, domain adaptation, and it lessens the catastrophic forgetting and shows good performance. Okay. Now concluding this research paper from the newer IPS 2021. Yes, okay. So we propose a continuing learning and the embedding space where neural network. Our method aligns with these distribution across tasks, ensuring that new tasks do not hinder generalization. Like we generalize well, we keep in check of the past dataset that we have learned, and we keep on adding new information to our data set, information to our model better. So it is mitigated catastrophic forgetting is mitigated through experience replay, which stores and replays information. Okay, our approach uses a simpler distribution estimation And we anticipate that better methods could further enhance performance of our algorithm.